Alright, so this is lecture 5. Get in frame there. And so we're going to talk about distance, norms, and of course the inner product in R3. So let me just get right to it. R3, of course, is a set of pairs of three real numbers. And I can do a couple things. One thing is, of course, I can take the dot product of v and w, right? v dot w, what is it? It's, in our notation, v1 w1 plus v2 w2 plus v3 w3, right? So I can take the dot product of points in R3 because I can identify points with vectors. Great. And I can also talk about the norm of a point in R3, the norm of v. And the most convenient way to talk about that is just to say, hey, it's the square root of the dot product of v and v, right? And then, of course, I can also talk about the distance between 2 points. So if I have 2 points, if I have point P and if I have a point Q, well, the distance between P and Q is what is it? Well, it's the norm, right, of Q minus P. In other words, the distance between 2 points in R3, it's simply the length of the displacement vector that goes from point P to point Q. So each one of these arrows here goes to show you that R3 has a particular kind of structure. If we take a vector space, all right, well, forget about vector space. Let's start with the last arrow, actually. The first shall be last, and the last shall be first. So if we have a D which has the properties that D does, in other words, what are those properties? What makes distance distance? Well, it's symmetric. The distance coming and going is the same. To mess with my son the other day, I told him it was going to take us 2 hours to get where we were going, but it was going to take 1 hour to come back. And he looked at me very confused. He said, no, that can't be. My son's intuition is correct. The distance coming should be the same as the distance going, at least for metric spaces. A metric space is a set paired with a distance function. Again, symmetric. Other thing, the distance between a point and other points only 0 when they're the same point. All right, so the distance from P to P has to be 0. And also the distance is positive for distinct points, right? It's 0 only for the points matching up. Those are the basic things. Let me look at my cheat sheet here for a second. Yeah, symmetric, non-negative. Oh, and also the triangle inequality has to be satisfied, which basically says that the length of a hypotenuse is less than the sum of the lengths of the. Well, anyway, there's a reason it's called a triangle inequality. I'll let you look it up. Not really the point here. Then, so a set paired with a distance function is called a metric space. R3 is a metric space. In fact, but open subsets of R3 are also metric space. Metric space doesn't have anything about any kind of linear structure. All right. A vector space paired with an inner product. Oops. I guess the first shall not be last. I don't know. I guess I'm just out of order. A vector space with an inner product, so the more abstract one of these guys is usually like this. And so sometimes I use that notation in here. If I use that, I usually say inner product, but of course the dot product is a specific example of an inner product. A vector space paired with an inner product gives you an inner product space. Inner product has to be linear in both slots, and you have to be able to pull real numbers out. You also have, so it has bilinearity. It also has symmetry. The inner product of v and w is the inner product of w and v. Of course, we know that's true for the dot product. It has to be positive definite as well. The only thing that gives you inner product of 0 with itself is the 0 vector. And so that's an inner product space. And then closely tied to that, there's this notion of a normed space. A vector space with a norm, so you can induce a norm from the inner product like that. And a vector space with norm, sometimes called a normed linear space, also a very useful thing to study. You can define sequences, and of course we can define open sets using the distance function, and closed sets, and we talk about convergence of sequence. We can say if every Cauchy sequence converges into the space, then the space is said to be complete. A complete norm linear space is called a Banach space. In fact, that's what we're working with. R3 is it's a finite dimensional Banach space. All right, but you'll learn more about that in your analysis course. I'm just throwing some terms out there. Now, so that brings us to what we're more interested in, of course, and that is, how do you generalize, or perhaps generalize is the wrong word. How do you steal? I think I like theft as a model of interpretation here more so. How do we steal? What's the theft of these to the tangent space at the point P for R3, right? So you remember that these are just the tangent vectors attached to the point P. So you think about it like this, or we also like to think about them, primarily we like to think about them as these derivations, right? So much writing. V1, V2, V3. Numbers. We're just at a point right now, so they're not functions. If we were allowing the point to vary, these would be vector fields. And in fact, everything I'm talking about we can also define for vector fields by just letting the point vary. But, how do you take the dot product? Now it's, so here it is. So the dot product of P, W, it's just defined to be V dot W, all right? The cross product of these two vectors at the tangent space to P. It is again a vector at P, all right? And you just take the ordinary cross product of the vectors. The norm, we don't really use distance in the tangent space, but anyway, it's important to talk about that. We are interested in distance. Anyway, so the norm of a tangent vector P comma V, it's got nothing to do with P, it's just the length of V. So basically, you already have seen this if you had a course in physics. We do this. We just don't write these P's all over the place, to be honest. We just say things like you can move vectors around. All right, great. Okay, so and then the usual formulas are true. You can prove carefully, for example, that Cauchy-Schwarz inequality is true, so the absolute value of V dot W is less than or equal to the norm of V, the norm of W, right? And that then implies that you can define theta between non-zero vectors, right? In particular, you have this formula, V dot W is length of V, length of W, cosine theta between them. I prove in the notes, and you're welcome to look at the proof. I will not force you to listen to me talk about it here. But V cross W squared, you can prove that that is in fact the length of V squared, the length of W squared, minus V dot W squared. And so once you have that identity, and you have this identity, it's easy to see that this must be, of course, length of V squared, length of W squared, 1 minus cosine squared theta. Okay, but what's that? Well, that's sine squared theta, right? So there you go. Length of V, length of W, sine theta, quantity squared. So that goes to show you that the magnitude of the cross product, the length of the cross product, norm of the cross product, whatever term you'd like to use, is just this. Let's see here. So, theta goes traditionally between 0 and 180 degrees. Sine's negative on part of that, so I should really put some, absolute value sign here just to be safe. All right. Anyway, great. And so all of the formulas you know and love from Calculus 3 about dot products and cross products equally well apply to tangent vectors at a point. Okay, nothing shocking about what I'm saying. Now we can also define vectors to be orthogonal, right? What does it mean to have an orthogonal set of vectors? Well, you know, S, a subset of the tangent space of P of R3 is orthogonal if V and W are in S. So I'm hiding the point of application. It's not written in stone that we have to write the point of application when we're working here. The fact that I've told you that we're there, I feel like is enough. Anyway, so V and W in S implies that V dot W is equal to 0. So that makes V and W orthogonal vectors, all right? If, you know, the length of V is equal to 1 for each V in S in orthogonal set, then we say S is an orthonormal set. Okay, so orthonormal sets are really, really important to our study in this course. An orthonormal set of 3 vectors at a point give us a basis for TPR3, because R3 is 3-dimensional, and we can easily prove that if we have a set of 3 orthonormal vectors, then they're linearly independent, and hence by the dimension theorems of linear algebra, they have to be a spanning set as well, all right, and thus a basis. Let's go through that. Not all the dimension theory in linear algebra, but let's go through that little proposition, because this calculation is important. So proposition, let's suppose you've got V1, V2, V3, and those are a subset of TPR3, all right? And let's suppose that Vi dot Vj is equal to the Kronecker delta ij. Now that's just a very fast way of saying that the dot product is either 0 if I is not equal to j, or it's 1 if I is equal to j. So basically, this says 2 things. One thing, it says that you have orthogonality, because it's 0 if they're not the same. But then inequality, well, what is Vi dot Vi, by the way? Vi dot Vi, remember, is the norm of Vi squared. It's the length squared. So if the length squared is 1 and the length is non-negative, that gives us that the length of Vi is in fact 1. So okay, so that's a good formula to express orthonormality. So here we got our orthonormal set. Then I need to give this thing a name. I'll call it S. Then S is linearly independent. All right. So how do we prove linear independence? All right. Proof. Usual thing. Suppose C1v1 plus C2v2 plus C3v3 is equal to 0. Then you take the dot product. With, say, the jth one, all right? So I got C1, V1, and I'm going to use I'm going to use an algebraic property of the dot product. I have not even written them down. I hope you can forgive me for that. But I do assume that you still know algebraic properties of dot products from your previous experience in mathematics. Let's see here, V3 dot Vj equal to 0. I guess I could make my notes even more boring and include all the properties of dot products. I just haven't gotten to it yet. All right, so there you go. Now, what survives here is only the case that, the only thing that survives here is when j is equal to 3, or when j is equal to 2. J can't be everything at once. J is either 1, 2, or 3. So if you think about it, that implies what? That implies that Cj times 1 is equal to 0, right? For j equals to 1, 2, and 3. But hey, that tells me that C1 equals to C2 equals to C3 is equal to 0. But it actually told me something, well, so there it is. So that's linear independence, hence S is actually a basis. basis for TP-R3. Now I'm claiming it's clear that TP-R3 is three-dimensional because I think it's not hard to show that, for example, this mapping psi, which goes, say, from the point P comma V, just strips off the vector part V. You can prove that psi is a bijective mapping from TP-R3, right, to R3, and you can prove that it's a linear map, and so therefore psi is an isomorphism. I know R3 has 3 dimensions, so that means this also has 3 dimensions, all right? So just a sidebar there. Okay, so it's a basis, so what? Well, there's another proposition, which is ever so very important. You know, if X is an element of TP-R3, and S, again as above, V1, V2, V3 is orthonormal set vectors. Of course, in TP-R3, then X is actually equal to, here's a nice formula for it, it's the sum J equals 1 to 3 of X dot Vj, all right, Vj, just like that. Now, the proof of that, very simple. We already know that S is a spanning set, so we know from our previous proposition and discussion that there exist C1, C2, C3 in R3 such that what? Such that X is equal to C1, V1 plus C2, V2 plus C3, V3, right? Then if you take X and you take the dot product of it with V sub j, by essentially the same argument we just went through for linear independence, we get what? We get Cj, Vj dot Vj, that's the only one that survives, the jth one, right? And that just gives us Cj. So, therefore, X is equal to X dot V1, V1 plus X dot V2, V2 plus X dot V3. This is my punishment for not writing the summation sign. V3, there you go. So we can, this is the, well, really is one of the fundamental importance of the orthonormal basis is we can select components with respect to orthonormal basis simply by taking dot products. All right, so obviously saying orthonormal basis, orthonormal basis, orthonormal basis gets old after a while, so we invent a new term. Oh no, forgive me, forgive me, forgive me. I think you knew that this was page 1. All right, so I think you won't be surprised when I tell you that this was page 2. All right, so page 3, let us define then definition, a frame for the tangent space to P of R3 is a set of vectors, E1, E2, E3 is the notation. Following O'Neill, I try to use that notation as much as I can. Set E1, E2, E3 of orthonormal vectors. All right. And then we define components with respect to this frame. I don't really have a standard notation for that, but if you have X, right, and you can write X as equal to a sum of, let's say, let's see here, oh goodness gracious, I guess F, upper J, J equals 1, 2, 3 of E sub J as the F1, F2, F3. Those are the components with respect to the frame, all right? Those don't have to be the same as the Cartesian coordinates. Cartesian components don't have to match these, all right? Now, if this is all at a point, all right? But if you allow the point to vary, you can talk about a frame along a curve, or a frame along a surface, or a frame along a volume. You pick it. A frame on all of R3, right? So you can allow P to vary, and you can get from a vector at a point, a frame at a point, to a frame field, all right? A frame field along some object. I won't try to write that all out, but you'll see what I mean as we use the language. It's very natural. Now, of course, obvious proposition here. Obvious proposition. Same terminology. What is the formula for the jth component? It is nothing more than x dot e sub j, right? Now, why is that true? Very simple. Very simple. Because if I take x as above, right? Oh man. Fine. We can take the dot product on the other side. I can save my mistake. So, okay. So EJ dotted with the sum of f upper j. Oh, bad form, bad form. Shouldn't really use j for both of these things. Let's say k. All right. Property is a dot product, distributive property. I can bring this summation outside, right? And I can bring these scalars outside, the f upper k's, and then I have ej dot ek. Now this is exactly the Kronecker delta jk because it's an orthonormal basis. It's an orthonormal. We use the term frame. Honestly, in a larger context, for me, a frame is really just an attachment of any basis, an arbitrary basis. So like, getting back to my Legos for a second here, I would say everything I'm showing you right here, right now, is a frame. Frame, 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 frame. All these are frames. Unless I was so unfortunate as to get all three of these Lego directions to be coplanar. It's a frame because it's a linearly independent spanning set of the tangent space. But in geometry, especially O'Neill's book, the term frame really means orthonormal frame. But as to not say orthonormal a kabillion times, we just call it a frame, which is a nice abusive language. Or maybe use of language, I don't know. But there's orthonormal. All right, now, so of course the Kronecker delta is a natural enemy to the summation, and out pops back. J is fixed here. K is the dummy index of summation. J survives. You want to be a free index. You want to be a dummy index. All right, there it is. And so there's the proposition. Of course, the dot product commutes. So right. Now, so components with respect to a frame, very simple. What are examples of frames, I suppose, is the next question you might ask, right? So let me just show you an example. Of course, partial x, partial y, partial z forms frame on R3. This, of course, is the Cartesian frame. So I guess if you want to be, in terms of at each p, I don't usually write this, but at each p, we'd have p comma, and what's the vector part? Well, it's 1, 0, 0, right? And then p 0, 1, 0, right? And then p, and then 0, 0, 1. Okay, so that's usually we use E1, E2, and E3 and linear for those. But this would be the Cartesian frame at p. So we will start to use a shorthand for that, but you should remember I do think of them when it's appropriate. I think of them as derivations, all right? I think of them as column vectors when it's convenient. So you should be aware that there are some identifications which be made, some really, well, isomorphisms between notations which are utilized, sometimes without saying sorry for that, but it's how I was raised. So this would, I mean, U1, U2, U3. If you want me to be more pedantic about it, it's U1 at P, U2 at P, U3 at P, but I try not to write the P unless it really matters because it gets really old. So there you go, that's the Cartesian frame. And in this case, if I had X, right, then in fact, in this case, we also know that, let's see here. Well, I mean, you could write x1, u1 plus x2, u2 plus x3, u3. So I do sometimes use this notation. If I use the same letter with upper index, it's my convention. I am referring to the Cartesian, the fixed, always existing Cartesian coordinate system we have to work with in R3, at least for the moment being. All right. Whereas I'm trying not to use that notation for a possibly non-standard frame. I'll use some other letter. All right. But of course here, there's a formula. I mean, x upper j. Of course, you could say, well, that's really x. X dot. Let's see here. Well, of course, it's x dot uj. I mean, that's what we're just talking about. But there's a little bit more you could do here. In particular, you could think about x acting, the vector field x acting on, say, the coordinate function x, right? And so that'd be like x1, u1 of x, right? Plus x2, u2 of x, right? Sorry, so many x's. x3, u3 of x. And if I was to do that, well, this, right, is just another notation for partial x, partial x. Of course, that's 1, whereas this would be like partial x, partial y. This is partial x, partial z. So 0, 0, and we just get back x1, right? So in fact, in this special case of the Cartesian frame, we actually do have other formulas which are kind of nice. xj in particular is just the vector field x acting on the jth coordinate function. So that's kind of something, a nice special thing to the Cartesian frame. I don't know. It may or may not be the case that an arbitrary frame can be realized. All right, frame. It's not really talking about frame field here, but it's actually a somewhat interesting and not altogether simple question to answer. When is it possible to identify a given frame as the set of derivations? All right, the set of like partial x, partial y, partial z for some coordinate system. All right. When does there exist a coordinate system such that a frame is in fact the derivations of that coordinate system? That's an interesting question, which we'll eventually come back to. Okay, so obvious next question, we like dot products. What happens with the frame and the dot product? Well, if you talk about a frame and dot product, right? So just get right to it. Proposition. If, let's say, V is equal to a sum f upper j ej and W is equal to a sum over I, let's say G upper j ej, all right, then V dot W is equal to just what you'd like, all right? So the analogous thing to the dot product for Cartesian coordinates, right? It's equal to a sum I equals 1 to 3 of f upper I, g upper I, all right? That was true. I mean, the definition in terms of the Cartesian coordinate system is that this is equal to a sum I equals 1 to 3, right, of v upper I, w upper I. But that's with respect to the Cartesian coordinate frame. Why should it be true for another frame? Well, the proof is actually pretty simple. So just by calculation, v dot w, so that's a sum. And of course, I'm assuming that the E1, E2, E3 is an orthonormal frame. That should be understood here, okay? So this, I'm going to drop some of the notation, dot sum gi. I should use different letters for the dummy indices of summation when I'm using them both in the same expression, otherwise it's bad. Begs some questions. So then I have a sum. And let's see here, so I've got these components, fj, gi, and then I've got ej dot ei. I'm using the properties of dot products here, all right? Which, by the way, are the same for R3 as they are for the tangent space of vectors attached to a point in R3. All of those standard arguments from Calculus 3 lift to the tangent space at P through that isomorphism, in fact, that I mentioned in the previous page. This is a Kronecker delta, ji, and what are we left with? You know, Figi, which is exactly what we claimed. So, all right, great. Orthonormal frames make formulas look like standard formulas, all right? You'd say, okay, well, that's great, but dot products are simple. What about cross products? How's that go? For cross product, there's something a little bit sneakier. Cross products, we need to talk just a little bit more about how a triple of vectors behaves under the cross product. All right, so suppose you have an orthonormal set of vectors. So let's talk about the cross product. All right, so suppose we're given, let's say, and I'll keep with we're transitioning to using E1, E2, and E3. All right, these are orthonormal, okay? At P, all right? So if you like, E sub j is an element of TPR3. All right. All right. The fact that they're orthonormal actually forces the cross product of any distinct pair of them to be the other one, plus or minus. All right? Let me show you why that has to be the case. All right? So that's a claim. Proposition. And I'm gonna prove the proposition for E1 and E2. All right? I'm gonna prove that E1 cross E2 has to be equal to plus or minus E3. All right? I'll prove that for you. But you could just as well do this argument for 2 and 3 or 3 and 1. All right? Now, think about this. E1 cross E2, what is it? It's a vector, right? So E1 cross E2 is an element of the tangent space at P of R3. But that is the span of E1, E2, and E3. Those are your only options. So that means that I can express E1 cross E2 in terms of the orthonormal basis, the frame. So that's E1 cross E2, dotted with E1, and then I'll put in something in different color here in a second here, plus E1 cross E2, parentheses dot E2, I'm put something else in a second here, E1 cross E2, dot E3. All right, those are all scalars. Those are the components, right? Those are the components. The actual vector part, right? I haven't written yet. So E1. This is just the orthonormal basis result applied to the specific vector E1 cross E2. Aha! Well, now we've got something, you see, because look at this. There, maybe you remember this, maybe you don't, but there's this triple product identity, right? This is equal to, what is it equal to? It's equal to E1 cross E1 dot E2. Now, I guess I have to be careful. If I have not permuted them in the right order, I won't get that. But because I've got a 1 and 1 and a 2, this has to happen. Anyway, it's plus or minus this. I don't really care. Because when I see E1 cross E1, 0, right? Same goes here. I can permute these until I've got E2 cross E2 by the triple product entity, which allows me to do cyclic permutations of the vectors that are in the triple. But let's see here. So if I just push E1 2 spots over, then I'll have 2 and 2 in the cross product. So I think it's actually plus. I don't think I need the plus or minus there. But anyway, the point is that's 0. That's 0. This is the only thing that can possibly be non-zero, right? So this little thing I did with the triple product and it doesn't work over here. And then, well, what else do we know? We know that E1 dot E2 is equal to 0, right? So that tells me that the angle between them is 90 degrees. But then the length of E1 cross E2 is equal to length of E1, length of E2, sine of 90 degrees. Aha! Well, that's 1. Right? So how can I have the length be 1 here? The length of this is 1. So I've got a vector of length 1 dot with E3, right? So a vector of length 1 dot E3 gives me 1 times the cosine of the angle between, well, let's see here how to argue this. Maybe I need the, I guess I do need to know, that E1 cross E2 is in the E3 direction. How to say that? I guess there may be a small gap here in my argument. Oh, wait a minute. I've got E3 dot E3. I somehow get to E3 dot E3, E1. Oh, I'm sorry. I proved something a little bit, my assumptions for the thing I'm looking at in the notes are a little bit different. Here I'm not given that E1 cross E2 is E3. I'm saying that in fact by, I need another little lemma that E1 cross E2 is in the direction of E3 in order to get the plus or minus 1 here. It's kind of a moot point because I'm going to assume something in the next bit, so I'm just going to leave that little, a little missing bit there. I'm sorry, but certainly the argument I showed you here shows you that E1 cross... Oh, I'm sorry, I'm an idiot. Look, this formula right here actually is itself proof that E1 cross E2 has to be in the E3 direction. It shows that. So since E1 E2 is in the E3 direction, and the length of E1 cross E2 is 1, that leaves the possibility that this is either plus or minus E3, basically. So then this gives you, of course, plus or minus 1, right? Oh, well, plus or minus E3 is the bottom line. All right, so that's it. So finally, let me stop quibbling over. If there's something missing, you'll have to go back to the theory of orthogonal complements and fill it in from there. I don't think so. I think we have enough without getting into the linear algebra of normals, normal spaces, and all that. Okay, so here's another proposition, a little bit easier to work with. If E1, E2, E3 is frame, and E1 cross E2 is equal to E3, then you also have that E2 cross E3 is equal to E1, and you also have that E3 cross E1 is equal to E2. All right. In other words, this single condition that the cross product of any distinct two gives you the third one in the proper order, in a cyclic order, automatically necessitates the other two cyclic cross products. All right, so I'll just prove the E2 cross E3 thing here. I'm including these details because I, at various points in my life, have tried to prove these things the wrong way, and they were very complicated. E2 cross E3. I mean, the hero here in my arguments is the use of the orthonormal frame. All right. So this is E2 cross E3 dot E1 E1 plus E2 cross E3 dot E2 2. This is just the orthonormal basis expansion. Of course, we can permute these by the triple product identity until we've got E2 cross E2 or E3 cross E3, so these pieces drop out by the argument we went through just a second ago here. And this thing, well, what's E2 cross E3? Well, we'd like to say it's E1. What do we know? Well, we know that E1 cross E2 is E3, right? So we have to use the triple product identity. So we're allowed to permute these in cyclic order. So let's see here. This is the same as E1, just move things to the right, all right? So this would be in E1 cycles back. So that's E1 cross E2 dot E3 E1. Aha! E1 cross E2 was given to be E3. So that's E3 dot E3 E1. So lo and behold, there you go, E1. So it's very similar. You can show that E3 cross E1 is equal to E2, all right? Now this is really nice because it means to check that a frame has this nice so-called right-handed property that the cross product of the first two gives you the third, and likewise these. It suffices just to check that the cross product of the first two is the third. Now, I guess you got another option, right? You could say the cross product of the first two was minus the third. That would give you what's called a left-handed frame. So a frame like this that has this pattern is said to be a positively oriented frame. Okay? Positively oriented frame, E1, E2, E3. Alright, that's a positively oriented frame. And you know what? There's a really awesome little theorem. Oh, by the way, all this stuff I'm saying up here, you could elegantly summarize as follows. Epsilon, let's see here, epsilon I, J, K, E, K, this is a very silly summation, some K equals 1 to 3, because, well, it's only a non-zero for one thing. So some K equals 1 to 3 is EI cross EJ. Okay, that's in short synonymous with positively oriented frame. That's just a quick way to write that the cross product of the first two gives you the third in terms of the Levi-Civita symbol. Anyway, so there's a proposition which says that if we've got V, with components Fi, and if we got W with components Gj, for a, E1 cross E2, and I'll be greedy, I'll do plus or minus E3. I'm going to cover the left-handed, this is an ambidextrous argument, all right? Then V cross W is, well, it's a sum ijk epsilon ijk fi gj EK, and you got a plus or minus there. And the plus and minus follows. If it's a right-handed frame, it's plus. If it's a left-handed frame, it's minus. Just like that. So, now the proof of this is very straightforward, very computational. Wait a minute, is it? I mean, I worked it out. Was it that straightforward? I don't remember. Yeah. Yeah, sort of. Alright, I'm done. Fine. Here's the proof. So, V cross W. Now, this is, by the way, the formula in Cartesians is the same, but with VI here and WJ here and no plus or minus, right? That's the standard Cartesian formula for the cross product. Anyway, getting back to our other one. So I'm just going to go ahead and use distributive property to pull out the sum over I and the sum over J, all right? And we've got Fi, Gj, and we've got our EI cross EJ, right? But then, go back to the definition up here, put that down there, and lo and behold, there you go. Sum IJK. Oh, and I forgot the plus and minus when I put this in, right? So, long story short here, if we use a frame, the formula for the cross product and the formula for the dot product stay the same for the new components. So perhaps you proved properties for dot products and cross products in terms of components before. If you did that, then those arguments you went through transfer over here just the same. I mean, cross product and dot product has all the same properties it did before in Calculus 3. All right. Let's see here. I guess I will show you, if you don't mind, I'm going to go ahead and use my notes a little bit because I don't feel like writing all this out at this point. So here's a example right here. Here's any point P, whatever you like. I can take E1 and 2, E3 to be this constant frame. 1 over root 3, partial x, partial y, plus partial z. 1 over square root of 2, partial x minus partial z. 1 over square root of 6, exciting. Partial x minus 2 partial y plus partial z. You can take the dot products pairwise of any of these dudes and you get 0. For example, E1 dot E2 ends up giving me 1 minus 1 divided by the square root of 6, but 1 minus 1 is 0. E1 dot E3 ends up giving me a 1 plus 1 from the z in the x term, and then minus 2 from the y, but 1 plus 1 is 2, 2 minus 2 is 0, so 0. And then the length, well, the length of this is obviously 1 because you get 1 plus 1, square root is 3, divided by square root of 3 is 1, and likewise for the other. Here you get 1 plus 4 plus 1 is square root of 6 for the length of just this, and so it has length 1. Now, that notation is kind of a drag sometimes, so we like to use this U1, U2, U3 notation instead. This is either you could think about it as a fixed frame at a particular point, or you can think about it as a kind of a boring constant frame. It's like, it's always the same wherever you attach it. Here, or here, here, here. That's not very exciting to look at. Well, anyway, you get the idea. The frame stays the same. Okay. There are more interesting frames that are associated with coordinate systems. For example, the cylindrical coordinate frame, E1 cosine theta U1, E2 minus sine theta U1 plus cosine theta U2, E3 is U3. In Calculus 3, I call this thing R hat because it points in the radial direction increasing. I call this thing theta hat because it points in the direction of increasing standard angle. That's a frame. Another interesting frame to think about would be the spherical coordinate frame. Spherical coordinate frame is a variable. I can define that on R3. Okay, modulo the points where the spherical coordinates don't quite gel. Got some trouble on the z-axis, I suppose. Anyway, so modulo the usual concerns about degeneracy of angles and so forth. Here's a spherical frame. I guess I can zoom in a little bit more. The spherical frame, right? Well, the first one points in the direction of increasing spherical radius. This points in the direction of increasing, I think it's polar angle. And here's increasing standard angle. Alright, so that's the same as we saw before. So a spherical frame is somewhat complicated, but if you've taken much physics, you'll see that this greatly simplifies calculations in problems that actually have spherical symmetry with them. I should warn readers of O'Neill that O'Neill uses a different system of spherical coordinates. Just to illustrate what's the difference. Well, so here's the spherical coordinates I use. If I pick a point, right, then I project that point down to the xy plane. If this is the x, y, and here's z, right? So this would be the standard angle theta measured like that. If the, let's see here, the line from the origin out to the point in question P, well, the polar angle would be this guy, right? We usually use phi. Now in physics, they tend to switch the definitions of these fun. But anyway, this is not physics, this is math. All right, so great. O'Neill likes to do something more like, I believe his theta is the same, all right? But here's where it gets wacky. And, well, he's more of a geometer than I'll ever be, but he likes to do like this for phi. So his phi goes from minus pi over 2 to pi over 2. So pi over 2 is like here, right? And then the negative z would be at minus pi over 2, right? Our phi usually sweeps from 0 up here to pi down here. I mean, so, oh, tell me I haven't. Of course. Wouldn't be complete without me doing that, would it? Idiot. All right. So here was what I was just talking about to myself. Idiot. All right. Okay, so this is all pretty standard stuff. I'm going to stop this here for now and pick up in a second. Next thing we'll talk about will be the attitude matrix. If you're keeping track, I'm basically at page 31 in the notes right now, or halfway through section 2.2. Thanks. So this concludes lecture 5, part A.